Right, lecturer, Hui, and you can call me Lewis. Okay, so this is a presentation for a test number 2.3D. Alright, so this is about the document analysis and recognition. Basically, we're gonna recognize the words and the text inside um, a word image, a image of a document. We turn it into words and paragraphs. Alright. That's basically what it does, and what we're gonna do. Alright. So this is a Jupyter notebook that I did. So so that the presentation gonna go more smoothly, and the submitted file is this Python code, but I turn it into a notebook. Okay, so you and I are it's easier for us to follow the contents. All right. Okay. So I'm going to go through this notebook. So for the first of all, we need to import some libraries that we need. All right. And for the next one, we're gonna talk about some of the functions that we used in this text. So for the first one, there are pawn extraction functions their functions to extract the candidate pawns. All right. So they have three-man strategy, and so I'm gonna explain what this strategy does. All right. So for strategy A, basically we're gonna use all the foreground pixels as a candidate pawns. So basically we just use the copy function to get off that. Okay, so next for strategy B, connected component centroids. Okay, so we have centroids here. What it basically what it does is that it calculates the coordinate of the centroid of the word, and it's gonna place a white pixel at that exact location. So it's gonna do it gonna drastically reduce the number of candidate points. Okay, so we're gonna see later from the example down below. Okay. All right. And for strategy C, which is maximum Y coordinator point per connected component. Yeah, okay, so as you can see, that C and B are they're kind of the same. It also place a single pixels at every component, every connected component. But the way strategy C check for the coordinate to place the point is just different. We just select the maximum Y coordinator of each blob, which is the lowest pixel of the blob, to place a Y pixel there. Okay, so these two work kind of the same, and yeah, they also use a same function from the library. So these two work really the same. Alright, so next we're gonna talk about how we gonna load the document. Yes, this is just loading document and transform it a little bit. This is for threshold 200, and this is a negated image. Yeah, we basically just get the UR 255 to minus the dot binary to bypass it. Okay, so that's basically it. This is just loading and bypass the image. Okay, I'm going to talk. Here's are the example of applying the three strategies that we have talked about. Okay, here. So as you can see right here, for strategy A, we got up to 175,000 pounds, which is a lot. And for strategy B and C, yeah, I've told you that the way these two strategy works are kind of the same, so we got the same points as well at almost 4,000. This 3,900. Okay, so this is an example of applying it to the document. Alright, next one is about the Huff transform. So I'm going to go back to the Huff transform function right here. Alright, so this is a Huff transform function. Okay, first we need height and width. We have the coordinates. Okay, so we're gonna get the lines first. So when lines are detected in Huff space, so each line returns we're gonna return a polar representation. Okay. Then for each line, got angle, median angle, and skew degree. This is for for the angle that outside this bound. We're gonna like normalize it to like prevent the upside down rotation. Okay, this is the code for prevent the upside down rotation. Then we're gonna like create a 2D matrix. Basically what it's gonna return from this function is a 2D rotation matrix. We use the get rotation matrix 2D here. Yeah, and applies the bicubic affine transformation with border replication to like skew the image. So this is what we get. So this is a part that we apply the grid transform function. We use 3 different threshold from 10, 15 to 20. Okay, see from strategy A, all the skew are -7 degree. The times are really high. So you can see the Huff time here is usually around above 40 milliseconds, but for strategy B and C, the time are significantly less. That for strategy B, the minimum we see here is only 4 milliseconds for threshold 15. Okay, so almost all the skew from B for strategy B to C are -16. But for threshold 20, the skew is -17 for strategy C. Okay, so we can see the difference in the Huff transform time when there are less candidate points, right? You can see here there are a lot less time in total. Okay, so another point is that we can see that the strategy B performs so much better than the strategy C. Okay, next I'm going to test it with some image online for more diverse test cases. Okay, so we have some image of, we have a research paper, invoice, we can pay, BAF document, store receipt with different languages, yeah, with different features too. And this is the skew after we using Huff transform. Okay, this is for test case. So as you can see right here, for the research paper here, the skew doesn't change much. Yeah, it doesn't rotate, but for this invoice and yeah, for the invoice it rotate by minus 10.5 degree, so it's very nice vertical, and it's easier to for the eye to read, for the text to recognize it. Okay, for this we've got the minus 17 degree. Okay, so this is the mathematical formula. Okay, this is written in French. This is French. There are noises in here. There are some parts that are a bit blurry. You can see. Okay, so the result is skewed by 12 degree. And for this store receipt too, this is more, it's minus 25 degree, which is skew. It doesn't change anything. But I guess they are like the structure of these are a little bit different. Yeah. So okay, here's the performance of it. This is the performance of it. Okay. So this part is about the comparison between a skewed and deskewed images when we extract the text from it, right? So we use the pi tesseract to actually extract text from the image. Okay, we got a duck here. We got a normal duck and we got a skewed duck, and we put them together and to use the image to string function, and this is the result of it. As you can see that for image are skewed, we can barely get any meaningful string here. That it doesn't make any sense at all. But for the skewed image, as you can see here, I can there are some part that not right, but overall it's way much better than a skewed image. See here, I can read it. It is minimal adversarial examples for deep learning on 3D point clouds. This is much more comprehensible compared to the skewed image. Right, so this is basically it. Thank you.